Hi, my name is Haoyao. I'm a second-year PhD student in the math department. In this video, I will present a Bayesian rank aggregation method in the context of peer and self-evaluations. Imagine you are in a class where students evaluate each other's presentations. So each student ranks their peers and also themselves. The instructor wants to fairly combine these rankings to contribute to the students' final grades, as well as to understand their ranking patterns. An important issue in this setting is that people often overrate or underrate themselves. A common solution is to remove the self-rankings altogether. The problem is that this may discard useful information, especially if the self-bias could be indicative about a ranker's overall competence. So our goal is to investigate how much self-bias influences the final rankings and whether adjusting for it improves fairness. Therefore, we propose a method called BaseRank, which stands for Bayesian Bias Detection in Peer and Self-Rankings. Suppose this is a ranking matrix. For instance, if there are 5 people in total, the first column can go like 1, 2, 3, 4, 5. The second be like 3, 1, 2, 4, 5, and so on. Note that the diagonal entries are their self-ranks. Now, the ranking data are ordinal, meaning they only show preferences of the rankers, but not the absolute performance levels of the presenters. So we introduce a latent importance score omega, which is a continuous variable that maps the observed rankings to an underlying performance scale. Now, omega is a quantifiable measure like height or weight. We break down the latent score omega into 3 components, which are the true performance mu, the self-bias beta, and the noise. To estimate these components, we assume the true performance, mu, and self-bias beta follow normal distribution, respectively. And since we have little prior information, we apply non-informative hyperpriors to these parameters, which leads to the Bayesian hierarchical structure. And the posterior estimation is carried out using Markov chain Monte Carlo simulation. To evaluate base rank, we test it under different conditions and compare it to other methods using 3 metrics. First, the Spearman correlation between estimated and true ranks. Second, the probability of identifying the top performer. And then the top 3 coverage rate. As the bias effect increases, at some point, everyone just ranks themselves as the first. Simulation results show that even in such extreme cases, base rank provides stable and fair estimations. Also, base rank is constantly among the top performing approaches. To demonstrate base rank in practice, we analyze peer and self-evaluation data from a graduate level class with A teams. We computed the aggregated ranking by different methods. It shows that the top and bottom teams are consistently agreed upon by all rankers. Now, base rank allows us to explore what is going on. By examining the posterior distributions, we observe clear performance clusters. For example, the top team is distinctly better, while the teams in the middle are statistically indistinguishable. This reminds us that it may not be fair to simply claim who is better than whom. The model also estimates self-bias for each ranker, which verifies that most teams have positive bias towards themselves. And we also find that students who perform better tend to rank others more accurately. To summarize, base rank provides an unbiased and interpretable solution, which thus enhance fairness, transparency, and reliability in peer and self-evaluations. Thank you for your listening.